All right. My fellow scientists and honored guests, for those who don't know me, I'm Timothy Lang from NASA Marshall Space Flight Center, and I'm president of the AGU, Atmospheric and Space Electricity Section, or ASE. Today I am honored to give the introductory remarks at the AGU Benjamin Franklin Lecture. This biannual event honors the life and work of Ben Franklin. There is little I can say that hasn't already been said about Mr. Franklin. He's founding father of the United States, ambassador, newspaper editor, inventor, and scientist. The list of his life's activities is boundless. In our field of atmospheric and space electricity, he is best known for the invention of the lightning rod, and of course, the famous kite experiment that demonstrated the electrical nature of lightning. Now, apropos of many results in our field, that particular experiment remains controversial to this day. After all, Thomas Francois Dalibard did it first. Nonetheless, given the monumental historical significance of Ben Franklin, it is only fitting that this lecture have a strong historical perspective, and that those who give it play an important role in the recent history of the field. I would like to thank the 2017 ASE Franklin Lecture Committee, Phil Kreider and Earl Williams, both past Franklin honorees, and Mary Beth Stolzenberg, who is also lecture co-chair. Unfortunately, she couldn't make it today, and ASE President-elect. I also thank those who went out of their way to nominate their peers for this honor. Out of several worthy nominees, the Franklin Committee has selected Hugh J. Christian Jr. to talk to us about 50 years of lightning observations from space. Now, there is no better choice to speak on this topic, as Hugh has led or helped lead the development of the optical transient detector, the lightning imaging sensor, and the geostationary lightning mapper, among several other ground-based, airborne, and spaceborne lightning sensing instruments. Moreover, there is no better time for his lecture, with first light occurring for Hugh's technological children, ISS LIS and GLM, just this year. Now, Hugh received his bachelor's in physics at the University of Alaska in 1967. After a stint in the US Navy during the Vietnam War, he attended graduate school at Rice University, where he received his master's and doctorate in space physics and astronomy. By the late 1970s, he was working as a physicist at New Mexico Tech. In 1980, Hugh made the move to Huntsville, Alabama, to work at Marshall Space Flight Center. Hugh remains in Huntsville to this day, becoming a research professor at the University of Alabama in Huntsville when he retired from NASA in 2006. Now, back in 1989, Hugh led a paper titled "The Detection of Lightning from Geostationary Orbit." It took nearly 30 years since that paper, not to mention many years of preparatory work before it. But Hugh, it finally happened. Folks, please welcome Hugh Christian, the 2017 AGU Benjamin Franklin Lecture.
It with here. All right. And do I have a? And then what's this? If you want to get. All right. Okay. Well, Tim gave you a good background on Benjamin Franklin, so I will just say to have him in even more awe. He was born to a poor family in Boston, poor working class family in Boston, and sold by his father into indentured servitude as a young lad. No. Is this better? Okay, how's this? Hey. As I was saying, Benjamin Franklin was sold as a young lad into indentured servitude by his father, where he had to serve his older brother, and that's where he learned the printing trade. He didn't last very long in indentured servitude because he ran away from Boston to New York and got jobs in printing, and then he followed that up to getting moving to Philadelphia, where he continued to get jobs and eventually operated his own printing shop. He did a number of amazing things, including identifying, as Tim mentioned, identifying lightning as electrical. He also assigned the charge of the electron to be negative, much to the chagrin of some modern lightning scientists who have a problem with the sign of electric field versus potential gradient. Anyway, what I'm going to talk about is a long, long history of observing lightning from space. It really starts with the first space-based observations. In October 4, 1957, Soviet Union launched the first artificial satellite into orbit, Sputnik 1. It was a beeper that operated on batteries for 21 days. 4 months later, the US launched the Explorer 1, which had a number of instruments, including high-energy particle detectors supplied by Dr. James Van Allen. And that and follow-on experiments led to the identification of the Earth's radiation belts, for which he was named. 2 years later, Taurus 1 became the world's first weather satellite. 1 solar cycle later, man walked on the moon. By 1965, there were reports of lightning detections from OSO 2. Why the early interest in space-based lightning observations? Global lightning activity was very poorly known back in the day. The global distributions were based on thunderstorm days, which was a thunderstorm heard by one observer in a given day, so one clap of thunder was as good as 1,000. Very, very sparse data, inconsistent observations. The global flash rate was poorly known. It was calculated from one thunderstorm in England and using isokinetic maps by Brooks in 1925. Space provided an obvious means for viewing the whole globe and directly measuring lightning flash rates. At this time, there were no long-range ground networks available to the research community. This is a picture of the maps that Brooks used in 1925, and you can see that it's amazing he got as close as he did to identifying 100 flashes per second. This is a more updated map, right around the time that we started actually getting some space-based observations. Here's a list of some of the early observations. As you can see, there's OSO 2, there's Vela. DMSP had a series of instruments, and there were also some RF instruments, of which I'll talk about a few. The Orbiting Solar Observatory had photometers on board. It was very sensitive. It can operate only during the moonless nights, so it's very, very limited in when it can observe, but it did detect lightning, about 7,000 flashes over its lifetime from about 1,000 storms, which is significant to start the initial plotting of a global distribution. Vela, on the other hand, was very insensitive. It was designed to detect nuclear bursts. And to people's surprise, it did detect lightning, but only the strongest lightning flashes. And this led to the discovery of lightning superbolts, as identified by Bobby Terman. And these were flashes that he called that were more than 2 orders of magnitude greater than normal and exceeded 10 to the 11th watts peak power, optical power. Following that, there was the Special Sensor Lightning, SSL, which was flown on the DMSP satellite. It was the first one to have more than just one field of view. It had 12 regions it tried to view. Next in line came the series of piggyback experiments by Terman and Edgar. And they used single photodiodes, but they did have some background subtraction. Very limited electronics because they had very little resources available to them on the DMSP satellite. And they made measurements at dawn and dusk from synchronous orbit. One of the interesting RF satellites was the ionospheric sounding satellite, ISSB, which measured radio sources at 4 different frequencies, and thus was able to use the iris effect, which depending on the angle of incident, different frequencies were passed at different work, and so they were actually able to get some location information. This is a picture of the field of view of the SSL and the PBE, both very large field of views, with the downside being that they would have to integrate, to see lightning in daytime, you had to integrate very large cloud fields, which made the signal-to-noise ratio very poor, so you can detect only the strongest lightnings. This is a picture of the distribution of lightning on the Earth from the PBE experiment at dawn and dusk. Here's a picture of the distribution of lightning discharges from the ISSB. As you can see, they're both quite crude, but certainly better than thunderstorm days. And then getting better was Dick Orville and colleagues used the line scan sensor on board the DMSP. At midnight, we're able to see streaks of light caused by lightning saturating the sensor, and they were actually able to locate lightning flashes to within about 100 kilometers, and thus produce the best lightning distribution map of the time. So I went through the literature and looked at the various flash rates they predicted, and I plotted up on a time scale, and much to my chagrin, in the 1980s when I started working on this, I was worried there might not be any lightning left by the time I was able to put an instrument in space. Well, a real change occurred with the NASA getting interested in trying to make lightning observations from space with dedicated optimized sensors. And a workshop was held in Tennessee in 1979. And here is a picture of some of the individuals in that workshop. And I just want to point out a few, if I can turn this on. I got it. Right about over there, and right there, there's the great Mark Spruill and the great Bernie Vonnegut. Most of the leaders in our field, and they were giants, were at this workshop. Here's a fellow named Jim Dodge, who was at NASA headquarters, and he was a huge supporter, and he made this whole by funding the work we needed to do to figure out how to build a lightning sensor for space. He was instrumental in keeping this program going. Back in here, you can hardly see it. He was his boss, Shelby Tilford, who at first was skeptical, but became a real advocate. And if he had actually stayed at headquarters a little longer, we may have been able to get a geostationary sensor up at least a decade sooner. And next to him, I think, is Bill Vaughn, who was my boss at Marshall, and who was a very, very strong advocate of lightning research from space. And he's in the audience right now. Bill. Also, there's Dick Orville, who might be the only remaining people of this whole group who are still active in scientific research. That shows you how long ago. Notice that everybody's in a coat and tie. It was a different era. So what was the outcome from this workshop? There was strong agreement that NASA should go ahead with the program. Some objected to the word need, but they all agreed it was a worthwhile thing to proceed. 2 committees were formed. One to look at RF techniques, one to study optical techniques. And what was clearly necessary is that all the satellite sensors up to this date were not sensitive to let you know what the low-end thresholds were for lightning detection. So you really needed to have a better understanding of lightning, what the lightning optical signal looked like from above top of clouds. And they recommended the initiation of a U2 program to fly over the top of clouds, which we proceeded to do during the mid-'80s. And in fact, we just revised that to make optical measurements above clouds this past spring, part of the GLM validation effort. Also, Phil Bitzer was born a few days after the workshop, and obviously he was destined to study lightning and work on the GLM. Because the GLM took a long time. And because of this workshop, NASA went out and tried to hire for somebody, and they actually hired me. I was not attending the workshop. I was too junior in those days, but I got a job out of it, and I was there, and I've been in Huntsville ever since. So as I said, so the limitations of the early lightning space-based sensors was each detector viewed a very large area of the Earth and thus compromised this daytime performance. When you integrate the light reflecting from many, many clouds and you get lightning only from one cloud, you have a very poor signal-to-noise ratio going on. All the light reflected from the clouds, it's basically a Gaussian, and it goes as a square root. But still, when you have too much background energy, photons, you cannot detect them in daytime with any high detection efficiency. So that was needed. So we needed some way to get more than a few detectors. We needed to have an array of detectors to be able to actually improve. And then other techniques were needed to really limit the cloud photons. Well, two technological breakthroughs happened in this era. One was the development of the charge-coupled device invented by Boyd and Smith, and they received a Nobel Prize for this development. It led to, the CCD led to the development of solid-state cameras. Now we have CCD and CMOS cameras, and ultimately the demise of film cameras. And it enabled the development of space-based lightning sensors that had high detection efficiency and good location accuracy. Another invention was the global positioning system. Launched in 1973, became fully operational in 1995. Civilian use in the 1980s, and immediately started having an impact on lightning research ground-based, because now you can build arrays of sensors and have good timing at each sensor, and you can have good time of arrival data. So you can all the ground-based sensors now are viable because of the excellent timing provided by GPS. So as I said, we basically instrumented a U-2 aircraft. We had to have well-calibrated instruments, and we needed to determine the intensity, the temporal, spatial, and spectral characteristics of the lightning. And the question at that point was, would it be possible to detect a large enough percentage of lightning flashes during the daytime to make it a worthwhile mission? We instrumented U-2, had a number of instruments on in the early 80s. This shows you a palette of some of the instruments that we developed and flew. So it's a picture of it. This is an eighth meter spectrometer, which was essential because we needed to have an idea of what the spectrum looked like above the top of the cloud to try to pick a specific emission line. And these were some of the optical pulse sensors we flew. And what we were able to put together was we were able to get a distribution of lightning flash energy. And we wanted to be able to operate down in this area near 90% detection efficiency. And that was the design goal of the instruments we went to space with. This was based in those days on only like 73 flashes. And we used this curve was the basis for designing the OTD, the LIS, and the GLM. So it was a valuable. We also were able to get reasonably good spectral data. And it became very clear that the spectrum in the ionized area of the spectrum was very variable, as you saw from space, but quite consistent in the neutral emission lines. And we ended up picking the 7774 because it had the attribute of being very narrow, and also it was the brightest of all the emission lines that we saw. So we picked that to be our design goal. Other experiments that went up shortly after the workshop was the day-night optical survey of lightning, which was a mission on the space station. It was PI by Vernie Vonnegut, and it was one of the it used Super 8 film camera to look at the lightning with and image the lightning. Maybe one of the last missions to use film for specifically motion pictures. So as I said, the issues were we basically decided optical techniques were far superior than RF for what we were trying to do. But we had to come up with techniques to minimize the background contamination by clouds, and we developed a number of different techniques. We decided to use a CCD imager. We wanted to go as fast a time rate as we can. The full width half max, so the optical pulses were about half a millisecond. We were able to design a camera that can do 500 frames per second, which is still what we're using on the GLM. and we developed very narrow band interference filters, 1 nanometer wide, to minimize the background. This is the idea of the trade-offs we did to get to where we needed to go. We wanted to have a spatial resolution about the size of a cloud, so we could maximize the signal-to-noise ratio, optical to background. We picked a near-infrared emission line, which is down off the solar curve a little bit to help. We went as fast as we can to make sure we capture the whole, integrate over the whole pulse. And then we developed a processor, which we called the real-time event processor. The original ones that we built for LIS and OTD were a hybrid analog and digital one. The concept was first developed by Chris Shelton from TRW, but designs were executed by Mike Stewart at UAH, and he designed both the LIS real-time event processors and all 56 of the parallel GLM event processors, which were all, by that time, electronics technology had advanced far enough that we can do it in all digital and make it a higher performance. This is this picture of the camera head for the LIS and the OTD. It shows you how, in those days, we were able to build things without quite as much oversight as we do now. And this was designed in the early 90s as part of the Earth Observing System. It turns out that we wanted to go to GEO right away, but we were having trouble. We tried to get on GOES-M, and they had limited resources on power and mass, and they ended up flying a solar X-ray imager because the Air Force wanted that because they were worried about astronauts on the shuttle going on polar orbits. Of course, never had polar orbits, but that's why we weren't able to get on GOES-M. And in reality, the technology wasn't advanced enough. We couldn't have built the instrument. We could barely build it this GLM recently. It just shows you some pictures. There's doing our calibration. There's Mike Stewart. This is a picture of the first satellite we put up. It was the Orbital Sciences satellite called Microlab 1. This was where the GLM was located. On the other side, there was another instrument which is used radio occultation from DMSP satellites, so to try to get soundings of temperature and humidity through the atmosphere. It was a very successful little satellite. It used gravity gradient stabilization, which meant it didn't have much stabilization, so the pointing wasn't good enough for doing storm scale studies, but allowed us to do a survey of distributions. This shows you a picture of it in the lab. We're doing final calibration checking. This shows you it mounted on the Pegasus. It was flown with 2 other EarthCom satellites. And this shows you some kind of initial pictures we started getting. Here's the Korean Peninsula. You can see the gravity gradient boom getting in our field of view. And this is the picture of the first lightning we saw from it. And you can see as the satellite moved, you had one cell, and you just got a streak of lightning going from it. So we were very pleased how well it worked. This is now and by the way, the optical transient detector OTD was one of the cheaper, better, faster. We had 9 months to build it. It was originally was an engineering model for LIS, but we were able to get a flight on that, and we actually delivered that in 9 months. It's one of the few golden era faster, better, cheaper that actually deserved its name. This is a picture of the LIS telescope, and this shows it mounted on the TRIM satellite. There's LIS. All this is a phase array radar built by the Japanese. The satellite was built by Goddard, and it was wonderful because it had a number of different instruments that we can compare our lightning measurements with, both radar data and microwave data and radiometer data, and it lasted from launch in 1997 until 2016, which was for a 3-year mission. That was pretty remarkable. This just shows you the comparative orbits between the two. The OTD was in a near polar orbit. The TRIM was in really a tropical, more of a tropical orbit. Well, some of the advantage of observing from space is you do have the high ground. It's a great vantage point where you can view large areas, observe total storm systems. The lightning shows all kinds of different processes. Excuse me, I'm sorry. Yeah. You can be used, because we have energy from the light, the electrical energy that's generated by a thunderstorm is strongly coupled to the lightning production, strongly coupled to ice production, and the energy production increases in phase with the storm energy. So these are all points that make detailed observations very valuable. So what we were able to do is we started putting together maps with the distribution of lightning, and this was, and now we have it for almost over 15 years. This shows a composite map with 0.5 degree resolution, and it shows the very, very unique distribution areas where you have lots of peak, mainly lots in organic areas where you have mountainous terrain. For instance, here's a picture of that. You can see in South America, Africa, we called that the hot spot initially. The Belgian Congo had some mountains, and it basically made lightning all year round, and that's why it was the pronounced leader. And you can see very interesting along the Himalayas during the monsoon season, and in Indonesia, very high rates. But Rachel Ulbrich decided 0.5 wasn't good enough. So she did a 0.1 degree resolution lightning map, and it shows you the amazing detail here. And she then started picking out the real hot spots, and found out that in Venezuela, Lake Maracaibo, it was truly the hot spot, and she gave it the gold medal for producing lightning. Like 297 days out of the year it produced lightning. Amazing. So that you can look at the maps, we can vary them as a function of season, and you can see how the lightning migrates during the northern hemisphere summer, and then it goes down the southern hemisphere, and you can see because of the large landmass in the northern hemisphere, outside the tropics, the peak of lightning activity does occur in northern hemisphere summertime. We can also look at it, all the database put together, but in one day. This is in the local time, and you can really see the effect of local heating. The dominant source of lightning is by air mass thunderstorms. Even though big frontal systems produce huge amount of lightning over the course of a year, most of the lightning is produced by air mass thunderstorms. And you can see that all the land masses just heat up, same time, local time, like it's like one heartbeat of the earth due to the heating of the sun. If we look at the same thing, but in diurnal time, you can see a wave of lightning pass across the earth, which is pretty interesting. You can even see it start off in South America, and then as it goes westward, peak in North America. Well, we wanted to compare lightning and rainfall, and you can see here's a rainfall map from the TRIM using the radar and the microwave radiometer, and you notice it's a much different looking map than lightning. However, if you break the rainfall into various regimes, one for warm rain processes, one for convective process, and blue for stratiform process, you can see that the green, which is the convective process, looks very much like the lightning distribution. And in fact, there was a lot of research early on that said that lightning could not be used to look at precipitation rates. And this shows why. This is a famous paper by Peterson and Rutledge that showed various regimes. You get a lot more lightning, small amount of rainfall produced more lightning in arid areas than it did in maritime. However, Walt Peterson followed that up with using the TRIM data and radar data to look at just the precipitation above the freezing level. And we find out that the relationship between precipitable ice and lightning is regime independent, is linear. So lightning has a potential, when you look at total lightning, to be useful for ice phase precipitation estimates. Early on with the OTD, we got this picture of a supercell in which almost all the lightning was intercloud as opposed to the ground-based zone very much. And we saw this increasing and then this decrease. Now, we only had, with OTD, we can only view a storm for 3 minutes. With LIS, only 90 seconds. So there's no way we can continue to study this. Now, this relationship between intensification of lightning and storm development has been well known. It was well known from Workman's work in the 50s. But we thought this might be a really good indication of being able to follow the storm when you can see total lightning and see whether there's a relationship between the lightning signature and storms going severe. So, in a very important experiment, Earl Williams and Steve Goodman got together and went down to the Florida area and used one of the few networks at the time that could do total lightning. That was the KSC LDAR network designed by, and they used the NextSat radar to look at the development of the lightning activity versus the radar activity. And what they found was really interesting. They were the first to start identifying what we call the jump signature. This is where you suddenly see a huge increase in lightning flash rates prior to the storm going severe. In this case, a little over 20 minutes before tornado hit the ground, we see this jump. About 10 minutes before the tornado hit this ground, we see a sudden decrease as the storm's growing and then collapsing. Well, this study was carried out for many more cases. In fact, we started having LMAs all over in the research community all around the country. And so Kerry and Chris Schultz started doing a detailed study and looked at hundreds and hundreds of storms and found that this is a very consistent signature, that you see the sudden intensification of lightning, a jump signature that happens well before the storm goes severe. And their analysis shows that it gives you a significant increase in warning time over using just radars. And this study is probably one of the key areas that allows us to finally put a lightning mapper in geostationary orbit. There's lots of other things that we discovered with LIS and OTD data. One is shown here, is that the lightning we see over oceans is much different than what we see over land. You can see here, if you look at the, you might not be able to read it, but this is the area of flashes, the area of groups, number of groups, the intensity of the flash. All these were higher over ocean than over land, which really suggests that in high flash rate storms, you're getting earlier breakdown, and you have less energy involved with them. But when you have weak updrafts, slow charging, you tend to build up much more charge as a reservoir, and you get much bigger flashes when the flash finally happens. We were able to look at almost a 20-year climatology with LIS, and what we found is when you take care of everything else, that the basic result of our response was almost constant over the whole time. This was shown in a Franklin lecture earlier by Earl Williams, and it's in agreement with some other microwave measurements and balloon soundings and stuff, suggesting that there is theories that a small increase in temperature can lead to a very big increase in lightning flash rates. Well, certainly we're not seeing an increase in flash rates. So either that theory is wrong, or there has been not much change in temperature over this period of time. There's also theories that solar cycles will have a big effect on Earth's lightning. Well, we could look at the measurements over a whole solar cycle here, and we essentially have no response. So the solar flares and so forth don't seem to affect flash rates on a global basis. To give you an idea of how the LIS compared to some of the ground-based networks, this shows you strokes comparison with Earth networks on the global basis and on the US only, and it shows LIS picks up overall more events than Earth networks, but Earth networks is improving significantly as they add more and more sensors. So it's catching up. Some of the other satellites that have been flown over period of time is the fast on-orbit recording of transient events. This was a small Los Alamos spacecraft designed to measure transient events, including lightning. The payload consisted of RF and optical sensors, had two 25 megahertz tunable receivers, and a single 100 megahertz tunable receivers. And they detected many, many bipolar events with this system, as well as other types of lightning. It also carried some two different kind of optical systems. It had a photodiode detector, PDD, which was a single photodiode that lets them record the time history of the optical events, including pulse shapes and so forth, and other characteristics. And they had a lightning location sensor, LLS, which basically used the same design concept as LIS. They used the same CCD, drive electronics, lens, and filters, but they had their own real-time event processor. This represented the first case where you had an imager and a pulse detector flown together. Some of the other spacecraft, there was obviously ISUL, which looked at transient luminous defense. I'm really talking mainly about lightning flashes here, but this performance was well covered by Dave Setman in his Franklin lecture back about 7 years ago. There's many different, I'm missing all kinds of them. There's a lot of small sats, Sprite Sat, Firefly. Russians have a spacecraft up. There's recently, this year, we put LIS on the International Space Station. The Japanese flew another instrument on the International Space Station. And recently, this year also, the Chinese launched the lightning mapping imager. This shows you the picture of the GLMs. And it consisted of a number of instruments, including RF, but also some optical photometers. And you can see that they wanted to look at TLEs, and they compared the amount of TLEs they saw to the summary of lightning, and they came to the conclusion about 4.8% of lightnings generated TLE, but only 0.5% actually generated sprites. This is a picture of the lightning mapping imager from the China, which was launched this year. It was a regional lightning mapper, had two CCDs which broke into two different areas here and here, and it basically does a yaw flip depending on the season. And so for the northern hemisphere winter is looking down near Australia, and for the summer then it looks at mainland China. This shows a picture of their first lightning that they saw, shown right here. And it just shows an example of their lightning distribution and comparing it with precipitation. So now I'm going to talk about the geostationary lightning mapper, which we have put up. It was the first lightning instrument in geostationary orbit. Like I said, we originally looked at the concept back in 1980 from that workshop. So 37 years later, we got it in orbit, which basically was my career. It's basically area covered and processing. It's approximately 100 LISs. The LIS was used an array of 60 micron pixels, 128 by 128. The GLM uses 30 micron pixels variable that have 1300 by 1372. So it's a little over 100 LISs. It basically views the full disk covering North and South America and adjacent oceans. And in March 1st, scheduled, a second GLM will be launched. And so eventually we'll have coverage and goes east and goes west. And that coverage will provide all the way from almost the coast of New Zealand to the coast of Africa. Oh yeah, I'm sorry. This shows a picture of the instrument. It's quite a large telescope. The reason it's so large is that it has an entrance aperture of 11 centimeters, but it has a collimated space. The field of view is plus or minus 8 degrees, but to get the lightning triplet through a 1 nanometer wide filter, you can only go at maximum plus or minus 5 degrees. So we had to expand that entrance aperture to almost 20 centimeters to limit the to be able to use a 1 nanometer wide filter. One of the advantages of having that is that we also had a 2.8 nanometer filter in the front, as well as a solar rejection filter. And because the rate of change of the wavelength passage as a function of incident angle increases faster the bigger the angle, everything works fine to plus or minus 8 degrees, everything gets through. After that, we start getting a cutoff between the two filters, and this acts like a virtual baffle at about 11 degrees, no extra light, so it makes it really better performance during solar eclipse times. This shows you the picture of the person standing by. Here's the electronics box. Here's the lens assembly. And here it is mounted on the GOES satellite next to ABI. It just shows you that how large the interference filter had to be. And this is the oxygen triplet as actually measured from lightning, where you actually have pressure broadening. And so not all the 3 lines are not separated as well. And so the actual performance works better on axis because of the blending of the lines. We use a very unique technique here called variable pitch pixels. In other words, we change the size of the pixels as you went out from the center of the field of view. Basically, with the Earth curving away, the footprint gets bigger and bigger, but if you make the pixels smaller and smaller, you maintain a similar footprint, and it's shown here. We would change the size of the pixel by 2 nanometers as you went out. And then eventually about here, we let it go, and that's why the performance falls off and the footprint falls off near the edges of the field of view. This shows a view from goes east and goes west. One of the big advantages we had with GLM is that we have a much bigger bandwidth, so we can actually go and accept much weaker flashes at the expense of having noise. If you set your threshold here, this is the lightning you miss. But this is the background noise you pass. If you set your thresholds progressively lower, you take more and more lightning, but you also have far more background events. With LIS, we only had 8 kilobit data rate, so we basically had to set the threshold fairly high because we would saturate whenever we go over an really active storm. Well, with GLM, we have, even though it's 100 times the amount of pixels, it's 1,000 times the bandwidth. So we have plenty of bandwidth to work with. And this just compares the performance of an optical sensor looking at lightning from space is all about radiometric throughput. You got to get as many photons through the system as you can, convert them to electrons, and then you can process them with electronics. So this compares the GLM's radiometric characteristics with LIS, and you can see it's much further away, so LIS has a big advantage there. But we made the entrance aperture is 11 centimeters versus 0.33, so GLM has the advantage. The CCD on GLM has a 92% quantum efficiency. LIS had about a 60, and the overall optical throughput, this is all fused silicon, so we had more optical throughput with GLM. And the frame time on GLM was 2, is 1.8 with LIS. So all these add up. It makes LIS about a 20% more sensitive instrument before the fact that you can have higher event rates. GLM will be used for many, many things. Once it's operational, there's many scenarios, many of which we probably haven't discovered yet. And so we just speculated on a few. Of course, it's going to be used by the National Weather Service for real-time severe weather monitoring and warnings. It'll be used for climate modeling because we've proven with LIS that it's an incredibly stable instrument. Over the whole lifetime of LIS, its throughput didn't change by looking at clouds. We were able to verify that. And we'll do the same thing with GLM because we're co-located with ABI. So we'll be able to really verify that its sensitivity doesn't change over time. It'll be very good for weather warnings over the oceans, help you with lightning safety warnings, especially with long streaming events. It'll be useful for ice phase precipitation estimates, and it can act as a virtual radar when in remote areas where you don't have radar, don't have any way of knowing what the structure of the cloud is. To give you, put things in perspective, for nearly 20 years, LIS detected about 23 million lightning flashes. GLM exceeded that number in less than 20 days. It's a real bucket of data. The advantages over some of the ground-based systems, because ground-based systems are getting better all the time, it still has a detection efficiency better than long-range RF systems. High-performance short-range systems, of course, get better performance, but they only go out like a radius of like 150 kilometers. Uniform detection, it has uniform detection efficiency with very little distance bias. Its ability to estimate it's able to estimate the optical energy of the lightning strokes, which is the current is linearly related to the optical output. So this gives you an idea of how much energy the flash may have released. The ground-based networks are good at estimating peak current, but not total stroke energy. So that makes them very complementary. And GLM can detect continuing currents, which are the igniters of fires, and it gives you high-performance cloud and ground lightning over the ocean. Most of the long-range ground-based systems see primarily cloud-to-ground lightning. So let's take a look at a few pictures from the GLM. This is the first light picture. And by the way, all these movies were made by Sam Tillier and Samantha Edgington, and so from Lockheed. They're all Lockheed pictures. They just were kind enough to share them with me. This is first light. You can see here these lines. The RTEPs are not bootstrapped up on the background yet. They have to actually start making many measurements of the background before they actually bootstrap, where they have a good estimate, and then they can start detecting lightning. But you can see very rapidly they bootstrap it up. And this, as the light progresses, you can start seeing, immediately we start seeing lightning on the cloud tops. See right down here, you can see lightning. So this is anytime you have a new instrument that you see light for the first time, it's really exciting time. And especially because all of a sudden you know it's working right, which is good. It's an example of this is a time lapse running at a very high speed. You start seeing lightning along here. Star system in North America. You can see the sun rising. Notice along here, that's glint of sun reflecting off of rivers and lakes where the water is calm. We see very little glint over the oceans, although you can see brightening over the oceans. Do this. Now we come focusing in, and we see lightning here and along these frontal systems. Notice all the backside stratiform lightning. At these time rates, the convective regions stay lit all the time, and the sparkling stuff is from stratiform lightning. This is a picture of the GLM lightning on top of the ABI, which is very high spatial resolution. You can really see the overshooting tops of the clouds, and you can see the lightning superimposed right on top of the overshoots. And of course, because the light is happening deep in the cloud and scattering, we see blobs of light. We don't see channels on the top. We just see lots of blobs of light coming out of the cloud top. This is just a solar eclipse in the southern hemisphere. Just a dark line goes across there. I'll show you a better one here. This is the northern hemisphere solar eclipse last August. Notice the you can see a little bit of lightning in here. Is it happening? Oh, there it goes. I'm sorry. Okay. Here it comes. Here's the eclipse coming across. So we can actually see the shadow of the moon in our field of view. Amazon basin. It's starting to, the sunlight is coming mid-afternoon, you start seeing all these lightning on these cells forming and producing all kinds of lightning, persisting into the nighttime. CONUS storm system. This is the imaging from the GLM. We get updated picture sent down every 2.5 minutes. That's the refresh rate. And we see the lightning coming down, information every 2 milliseconds. Again, you can see that the persistent lights are where the convective cells are. The flickering light is where you have stratiform. The convective cells are actually flickering too. It's just at this time, integration time, they look solid. It's 1 week of GLM data over South America. It's really fascinating. You can see these storms persist for a long time. So, afternoon, start dying off at night. Afternoon, start heating. Storms pick up. And you can actually see at this stage, you can see the glint coming across here. That's where the nadir of the sun is. And we're going to look at a real-time flash now. We've been seeing things that are going at high speeds. Let's look at a real-time flash. There you go. This is another flash, real time. This whole flash, but we have a persistence on here, so you can watch the actual growth of this flash from here to here. That's about 300 miles in about 5 minutes. That means if you look at that distance and the time it took, or 5 seconds, I'm sorry. You look at the distance and the time it took, that propagation was about 10 to the 5th meters per second, about the speed of a typical liter. So in all, I'll go back and see that again. That growth is probably a whole structure of growth, starting down here, going from cloud to cloud, charge center to charge center, tapping charge out of it. And you can see the frontal system here. So there's just some pictures of lightning in northern and southern hemisphere. This is integrated over 20 minutes. Another one over 20-minute time. This is another one, 20 minutes of lightning activity. We can also have information on the brightness of these flashes. And this is the lightning power density. It shows the brightness over some period of time. And this is an interesting flash. Early on, we saw this big storm system. This is 200 seconds worth of data. This is the same data, 200 seconds from the national network, same 200 seconds from the Earth networks. And you can see that the national network saw 2912 strokes, Earth network saw 3917. GLM detected 52,100 events, which is approximately about 11,000 strokes. This is before we had it fully tuned up. So, what are some of the future space missions? Obviously, ASIM is going to be going to the space station. It's due for a March launch. The French have Taranis coming up. The Europeans are building a lightning mapper to go to GEO. It'll be launched in early 2020s. And GOES-S is going up on March 1 to give us views from both goes east and goes west. And there's many other missions, small missions coming up. So the future looks bright for new missions and for new discoveries. And I suspect that I may not be be present at the, I may not be able to present the Franklin Lecture on 100 years of lighting from space, but I would be surprised if the next 50 years failed to achieve as much technological and scientific advantage as the past. The future is bright as lightning. Thank you.